Yeah.
All right. So, welcome everyone. Today we're beginning with the last lecture of Philip.
Okay. Thank you, Andy. The last lecture, we dropped it off that stuff here. That quick summary is that using the microwave reflectometry type of the measurement, one can measure the inductive response of the superconductor and close the 2D superconductor through this kinetic inductance measurement. You can just kind of refer what is the superfluid stiffness of the 2D superconductor, and we measure the superfluid stiffness, the trilayer graphene, as a function of temperature and the gate voltages, such that we can present that across the superconducting dome of the doped correlated insulator, how the superfluid stiffness got changes. That's basically where I just stopped it out. And then the superfluid stiffness more like to follow the dome that can be measured by the transport. Note that transport TC of the 2D superconductor is very close to the BKT transition temperature. So more like that there's some kind of correlations between superfluid stiffness with the TC. We can understand that why this kind of shape look like, as well as this slope of this initial slope of the superfluid stiffness decreases. According to theory, the slope is deeply related to nodal velocity, or the nodal velocity versus the Fermi velocity ratio. So one can explain kind of both of this. What I argued is basically using the developed theory from cuprate, where the nodal superconductor already there is the way that compute how the superfluid stiffness changes when you have the nodal superconductor. So this is the zero temperature part, and this is the temperature dependent part. The argument here is that say zero temperature, the limits. Basically, if I just know that what is the dispersion of the band, original band, where that you give it the band mass, using the band mass with times of this the carrier density. So basically, that's my argument is, well, basically I'm extending the n over m type the ratio, which is the essential part of the superfluid stiffness. Of course, parabolic band, the m is fixed. But if it's non-parabolic band, then of course m do changes. And the way that we can compute superfluid stiffness is quite naturally just kind of think about the n times of the second derivative of the band dispersions and integrate over the k in the occupied. I think that that's naturally follow through the generalization of the parabolic band of this one. So this form I can see that. And temperature-dependent part is nothing but if I have the nodal superconductor, which means that now quasi-particle dispersion is nodal. And of course, there is nodal velocity as well as the Fermi velocity is constituting this the Dirac cone-like the dispersion of the quasi-particle energy spectrum. And then we can ask that at the finite temperature how we can populate this the quasi-particle into this dispersion. I think that's kind of the second part that what constitute of that. And just kind of do compute this one, you get this linear T dependence. I think there was a kind of bit of the discussion why the linear is kind of natural, but simply just kind of compute this one, you get the linear. And I have to actually think through that why linear is really natural. But nevertheless, just using this one, basically idea is if I know that what is the single particle dispersion relations to form the original band, in principle, I should be able to compute everything here and knowing that this what is nodal velocity, right? So idea is basically that we use a band structure calculation. Note that the band that we initially start with is at the already correlated insulating band, which means a symmetric broken band. So you have to think about how we can construct a symmetric broken band, and that the Hartree-Fock calculation of what is symmetric broken band. Potentially, this is a little bit overestimate of the electron interaction. I'm going to kind of discuss, and just using this band shape, in principle, we can explain that why that this shape is kind of quite natural, as well as that the dispersion also tells us that how the phantom velocity changes, and that more or less also explain that how this the slope got changes or something. So that is maybe qualitative, but the idea that we can just through that understanding these pictures. There's no reason that this is a kind of right picture, of course, right? There are many other reasons that why actually this the superfluid stiffness changes in this way. I would kind of first argue that, in fact, if you just look at the cuprate, very similar structures appears, and then underdop and overdop regime, there is kind of connections between the TC as well as superfluid stiffness that they're being measured, and they're probably steep picture kind of in between overdop and underdop need kind of different type of the idea work it out. So I think there are various ways they look at this the experimental observation. Now, one thing that I want to argue, though, is that since we measure the superfluid stiffness as a function of the temperature and the density, especially as a function of the temperature in all kind of temperature ranges, and being that this tri-layer superconductivity is a 2D superconductivity, so you can naturally think about maybe we can simply apply the BKT theory to see that just BKT transient temperature out of this one. The way they work it out is, of course, we want to kind of use the this simple formula here. So according to the BKT that theory, we know that if I know the superfluid stiffness temperature, superfluid stiffness as a function of temperature, when that the temperature is equal to the 2 over pi times the T BKT, when this satisfies that connections, then I should be able to find what is BKT transition temperature, right? In other words, basically, given this the functional form the experiment we obtain, I'm simply just drawing this the plane with the slope of the 2 over pi, and cutting that slope with this the measured the rho of T, and those kind of the line, the black line, the project into the temperature scale is basically what the BKT transient temperatures we can obtain, right? And that's kind of what I'm just plotting here now. So this green line is basically from the measure the rho of the T that using these connections, I just kind of plotted out what is BKT transition temperature, and this is basically BKT transition temperature we obtained from the calculations, right? And here that once you just do that, there are kind of few things that kind of really disturb us when just look at this. So first of all, according to the BKT transition temperature the theory, low superfluid stiffness will decrease up to the BKT transition temperature. But then after BKT transition temperature, we expect to see that the superfluid stiffness actually steeply goes to 0. But that's actually kind of not something we observe, right? I think whatever this is BKT transitions is still kind of going down more or less smoothly. We know that this might be just some of the experimental issues here, especially that once you get into high enough temperature where the sample start kind of develop finite resistivity or resistance in there. Now that simple model we use that my entire sample behave like the one single piece of the inductor or with the kinetic inductance is questionable. It's a combination of the inductance and the inductor and resistor. So in a sense, I have to just do the so-called distributed circuit model to do that. That required a lot of the fitting parameters. So we just didn't do that. So in some sense, this part of the data is not too reliable. So not seeing those kinds of stiffness drop is probably okay. That's the experimental region. That one of the really disturbing part is, in fact, the large difference between the transport, the measurement, transport TC versus this BTK temperature estimation we made here. The reason that this is disturbing is if I strictly follow this is my BKT transition temperature, what this indicating is above the BTK temperature, BKT transition temperature, I still have, well, theory expected, then I have the free vortices, right? But then even with the free vortices, somehow I have the zero resistivity in the sample, which actually is kind of rather contradicting. So we need kind of really reconcile that why there's kind of this huge discrepancy.
What do you mean exactly by TC? Because like in the old literature in the 70s, people I think
Yeah.
would often say there's a. I mean, they wouldn't have expected a big gap, but they would have said.
Yes, right. So TC, how did we measure TC? Is basically we measure, say IV. This is a V. So we send the current and measure the voltage there. Right. In the superconducting state, it's completely zero voltages, and some point and kind of rise. Then in the 2D superconductor, there's always some sort of power law behavior. From this power law behavior, that you can just extract this linear IV, and then from this linear IV, that where exponent becomes a 3, that's where that you can just kind of do. That's a
Okay.
Right. That will give you the BKT precisely in the definition. Now, practically, when we just make the device and measure the really small bias current, and then you can see that, let's say that this is as a function of aperture, that I'm measuring the resistance with a very small bias, then you will see that kind of zero and it kind of goes up something like this. Practically, the really foot of this one is basically the BKT transition temperature we estimate in that way. So practical manner, if you just look at the T curve, and very foot of this Arvos T curve that close to zero, that's you can identify the BKT transition temperatures. Right. So what I'm saying here is that huge gap between this one cannot be reconciled with whatever things we can just do there. Right. Okay.
Just to clarify, that green curve, that's
Green.
the one you're measuring in these.
No, green curve is what we measured from the row, through this one, and the blue curve is what I measured from the Arvos T.
I see.
Yeah.
I mean, because I think it would be very, okay, maybe I need to think about it. It would be very interesting if there's a material where there's so, like there's a regime in these 2D systems where you would expect
Sure.
superfluid density that's non-zero, but
I know that there's a fancy way that you can explain. Indeed, I think that the Ashwin and Aslam actually tried to kind of come up with some fancy stories about that. But rather than buying the fancy theoretical brief, yeah. Yes, no, right. Yeah, right. But rather than I just evoke that interesting physics there, I would say this is a little bit more mundane, and I believe that there's a reason that we believe there's a mundane part that we have to worry about is following way. It's more of the experimentalist fault, let me put it in this way. Note that we measure inductance, not the kind of the characteristic the shear activity inductance, right? So which means that I'm just measuring the inductance, and then to convert into the superfluid stiffness with this intensive quantity, I have to just normalize with my sample size, like length and width, like the resistance converted into resistivity, right? So we have to put this length and the width that just measuring from my size of the sample. But although the tri-layer is better than a twist layer, but still there's a kind of enough number of the disorders in the sample, right? And you have to deal with this disorder. What is it? If there's a disorder in the sample, when we just make the superconducting the transitions, either DC measurement or this AC measurement, basically in some sense AC conductance measurement, right? So that you have to deal with the disorder in the sample, and especially when the transition is happening, you have to think about the percolation path through the sample can be an issue. In other words, if I just presented my stories, this is my width of the sample, but once that I have the superconducting percolation path is going through, then I start to measure the zero TC, right? In the either DC or the AC measurement we are present. And the percolation path may not occupy the entire sample. And in fact, you may have some sort of filamentary type of the structures there. And this filament has effect width in there. So if I just kind of ask that, what is actually this width of the sample of the measuring the total filament width compared with my width, and how much actual correction I should make that kind of close down this gap, between the DC transport or the BKT the DC transport versus the superfluid stiffness. I need about factor of the 3, right? So which actually I would say reasonable numbers, right? So only 1/3 sample becomes kind of superconducting pathway that connecting this one, the contributing that this measurement. Then I can just kind of say that, well, that if I just make that effect of the 3 the correction, I can just bring these things up. I think that's a kind of one way I can explain that kind of difference in this this part.
And then, Philip, if you do
Yeah.
that, what is the ratio of the 0 temperature stiffness?
Yes, so that's basically that's part. Now, if I just do that, this is basically the what we are just kind of computing. That if I just say the TC of the 0 temperature of the stiffness and with that correction, now if I just compare with the 0 temperature limit that I just mentioned with the TC, that's about the 10% of the part, which actually tells us that indeed the corrections actually push us kind of reasonably strongly it's a kind of strongly coupled limit. If I just don't do that, basically this big number becomes even larger, right? So I think that's a part. Okay, so right.
Is it the strong coupling limit?
Yes, 10%. Yeah.
Then it's still TC over 4 pi RS is a small number.
Now that's an interesting part. What is what is a small means, right? I think that's kind of important part, right? But another thing that I can just kind of mention that is just looking at generally this curve. So I'm just looking at the TC versus rho S0. Then this one is basically without this correction, so that's why the effect of the 3 is there, right? But anyway, so the important part is they are kind of really nicely lines up, right? And in fact, it's overdoped and underdoped. They're kind of nicely lines up. And it's strongly reminds that it's very similar to the kind of cuprate type of things. Although the explanation is just making it kind of rather different, but nevertheless, phenomenologically, that we are just kind of the present VMR plots into the all doping ranges onto this sample. In fact, this behavior itself is rather robust across any different sample. I briefly showed the last time at the end of my talk. We measure this kind of many different samples in the similar way. And of course, this device, this data I showed you is one of the best samples. If you just don't have this best sample, if you just kind of plot in the very similar way we want to plot, they all kind of spread it over, right? But nevertheless, the important part is they more or less follow the very similar trend and then kind of this linear trend. Yes.
So is this, can you get this W star over W in the different samples, and is it the same number?
As you see here, that they may not be, right? So that slope is related with basically that the numbers. I think we get kind of somewhat different slopes in the kind of few different samples.
Correlated to some other
Not,
quality of disorder?
unfortunately, no. I think there's another easy way that we can have that. I wish that, I think maybe some sort of scanning probe type of things and complete kind of mapping out the sample, maybe. But unfortunately, part is all this sample, we need kind of put both the top and bottom gates to gate in the structure. So yeah.
Like, that quantifies disorder, like some transport in the normal state or something like that, that could relate?
Another easy way that we can give this the ratio. Yeah.
Another question.
Yeah.
So if you factor of 3 and then you return to this analysis of cutting the plane with this thing and looking for the BKT transition, do you then see a sharp decrease in stiffness, the new BKT temperature?
No. Yeah, because as I said, that kind of once you just push into the high temperature, my measurement, especially superfluid stiffness measurement, is not trustable because that requires a different type of model and more uncontrolled model that we have to do, right? Okay. All right, so that's basically the part. I just try to skip this part, but let me just show you one more thing that the associated educations that in the last time. Because our measurement can be done with the let's see, some controlled. We can just do this inductance measurement in the presence of the current flow, And this is kind of quite useful techniques because in the presence of the current that I'm flowing, that I just kind of measure inductance, in a sense that you can see the so-called this nonlinear the effect, which means that under the kind of current, especially that the superfluid stiffness got changes. And especially this technique is very useful that when you have the nodal superconductor, in principle that where the current is in the nodal directions and that the antinodal directions, you may see that kind of different type of the behavior. And in principle, this is a technique that one can use to measure the nodality, how many nodes we have, then where's the node, and those kind of things. Very preliminary study, since we actually don't have too many electrodes, we can do that, but at least with this nonlinear Meissner effect, we can also see that, that we can measure the nodal velocity and those kind of things. And I don't want to kind of go over the detail, but that's more like this, the more quantitative analysis can be done through this nonlinear the measurement. Okay. Now I want kind of to go back to these questions that what Andre mentioned about this the size of the superfluid stiffness itself, right? So let's look at stiffness at the parabolic band, and I claim that and like this the flat band graphene the graphene system. In fact, actually, I was kind of thinking about that problem a little bit more last night. So roughly saying that my band structure is look like this. If it is, doesn't matter whether it's electron hole side. This is K energies, and in this case, if it's electron-like and hole-like, and there's kind of some sort of band of singularity, electron-like turn into the hole-like. And what I'm saying here is this is my underdope and this is overdope, and that's kind of how we can explain these shapes and things, right? That's kind of the claim that that I made, right? Now, especially now we are dealing with the flat band, means that this width becomes really, really flat, right? But then whether it's electron-like or hole-like, anyway, that mass becomes really, really heavy. And you can see that this, because mass becomes heavy, or that at the derivative itself, it becomes kind of really small. Second derivative is small. So basically, this quantity becomes very close to zero. So in a sense of flat band system, we expect to see that this superfluid stiffness is very small, right? So that's kind of the first statement one can make. Now, how small is that the data? Okay, so I just convert that into the Henry here, and the reason that I just did that is it's not only our measurement. There are other groups also measured in the this superfluid stiffness in the Rayleigh graphene. So at the same time, we published a paper that there's the paper from the MIT group. They use a slightly different technique, but nevertheless, they also measure the inductive response of the sample and just kind of plotted out this their superfluid stiffness. And if you just compare this data, for them, there's a different way of calibrating the data, but effectively they also calibrating out this also all the disorder W over W settings. But after all that, they can compare this kind of data, they are about the same similar numbers. I think there are some differences, but not more than factor of the two, right? There's even older experiments. This measurement was done by the Ginny Lau's group at the Ohio State. They use a kind of rather different method. They're using this nonlinear current, and considering the critical current, it's a little bit more involved, and it was a kind of not a direct two-way, but nevertheless they kind of estimate the what is the expectation, and this number is also kind of rather similar. So I would say all three groups, experimentalists, using different technique per se, and that estimate the superfluid stiffness, that numbers are kind of more or less, they agree to each other. So I think that's kind of one part I can say, right? But if I just compare that number with the, so this calculation for flat band has a small width, and just using all the quantum oscillations and other type of measurement, you can just estimate what is a flat band width and simply compute that this rho sub s, and this dotted line that these two groups shows is a more or less this expected in just kind of flat band. So what we are seeing here is that this is the larger than flat band, And in some sense, that's kind of the agree with what I just briefly mentioned, that if you just use quantum geometry, and if this superconductivity is coming from the kind of topological origin, there is a lower bound of this the superfluid stiffness. Maybe that is kind of related with this largeness of the value. Now, if you yes.
How you determine the bandwidth from experiment?
One way you can just do that is you can just look at the quantum oscillation under the magnetic field. And the quantum oscillation will give you the effect, the Subnikov-Das oscillation will give you the effective mass estimation. Just looking at the temperature dependence of the Subnikov-Das oscillation will give you that, in a sense, cyclotron energies, right? Cyclotron energy contains mass, and that's kind of one way you can expect it. Of course, whether that is really, but that's under the magnetic field, and there are many things that you have to do that, but that's kind of the usual way. There are other type of estimation, more or less kind of agrees, right? Now, yeah. Good. Right. Now, okay, so that's a good point. Now, our theory colleagues actually provide us Hartree-Fock band, and you can see that, you know, I think this is a kind of really bare band with this all the 4 flavors degenerated. Now, of course, the superconductivity I claim that comes out from the symmetry broken band, right? So in a sense, there's no reason that I have to believe that this is a right band. In fact, if you just use Hartree-Fock band and then the band, the Hartree-Fock, the calculation provide us that bandwidth is about the 30 millielectric voltage, right? And if you just put that number, this one and compute that, as I mentioned yesterday briefly, it more or less matched with the shapes of the behavior in general. But note that this is a theory divided by the 10. So which means that theory actually overestimated or underestimated, actually overestimated what is the superfluid stiffness here, right? So, and there is also, it's believable, right? This is a Hartree-Fock calculations at kind of complete mean field, and there's no reason to believe that this, the superfluid stiffness followed it. But this actually gave us really interesting the questions, right? What is the theory we need to compute this the superfluid stiffness, right? So that is a kind of really big questions out there. We know that one simple pair band type of things underestimated, and that the other one is overestimated. So answer is somewhere in between. And someone believed that I think maybe this is where that you have to really kind of address this quantum geometric calculation, which actually can, in principle, give you that superfluid stiffness in the consideration of the proper interactions into the system. Okay, yeah.
So if I put the stiffness aside for a second, the bandwidth estimated from experiment, and this is presumably the bandwidth from Hartree-Fock, is more than a factor of 100.
Is that right? Okay, yeah, that's that, yeah.
Because this is theory over 10, and it's like 10 times.
Yeah. Okay, so I think factor of 100, or okay, factor of probably 50-ish, I guess, or something. I think right. That's a good fit. Yeah.
This is more than like Hartree-Fock.
Yeah. Okay. Anyway, so that's kind of where the part that I suppose to finish up then half of the last lecture, right? And if you remember that second part that I was mentioning is that I want kind of also discuss about the capacitive response of the insulator. So now I just changed the gear. So very similar type of the measurement. I'm just measuring again the AC response of my sample, but instead of superconductor, I will go for the complete opposite limit. Now dealing with the insulator, right? And the insulator I'm going to deal with is a superconductor, the quantum Hall system, because I want kind of start with something more kind of topological in there. And the reason that the insulator itself is also interesting was kind of well summarized by this paper by the Lacquer's group. And the idea there is that if you have the insulator and if you just measure the dielectric response under this AC excitation, this dielectric response actually contains kind of the very interesting information. Now, of course, you can just define again the AC conductivity in there. And if it is the insulator, but it is that say topological insulator with the Chern number, and then of course this the AC dielectric the conductivity contains this the real part with this whole conductivity is if I just kind of look at whole, right? But in the longitudinal part, if I just kind of put it there, it has the imaginary part of the conductivity, which means that this is kind of conductive, that capacitive response, right? And if we call this as kind of capacitance, the theory expects actually this capacitance that you just obtained is kind of related back with the kind of this Chern numbers. In fact, again, that type of the argument you can nicely the present in terms of the quantum geometric arguments, which actually is the main part of this paper. So experimentally, what could be interesting thing is that indeed, if I just have the quantum or the Chern insulator, that if I just look at the AC response, and in a sense that you can measure the dielectric response, or if you just measure polarization current and just get the capacitive the part of the sample, you may see that kind of relates back with the Chern number of the insulator, right? So again, the sample that I'm going to kind of use is the graphene. Part of the reason is that that's easy to implement this type of the experiment in the various ways. And once you just kind of get into the graphene, the story got a little bit changed because the reason that we get this the capacitance, the dielectric response contains the Chern number is again that you have this kind of excitation across this insulating gap. And note that in the massive system, all the Landau level, the gap of the separation of the Landau level is equal. So basically, that's the way that you get just kind of Chern numbers out of this one. But once you're in the graphene, where that the quantum geometric calculations, that you have to just think about all the transitions between the kind of all kind of different levels, where that the level separation is all different. So indeed, those kind of the Chern number that we expect it becomes is not exactly the Chern numbers of the particular Landau level, but that becomes effective Chern numbers. And as you increase this Landau level filling, those effective Chern numbers actually increase a little bit faster. It's kind of superly, nevertheless, is monotonically increasing, right? So that is kind of expectations we have. So can we actually measure at least this dielectric response that in the quantum or insulator, quantum or system that we can just measure in graphene, whether we can just kind of measure those effective Chern numbers. That's experimental the procedure. Now, when we get into the quantum system and trying to measure this AC response, of course, this has been long history over the time. And quite early on already, this is the Dan Zui's group's work. They can just measure, they simply put the interdigitated or just two conductor and just measure the AC response. And they are seeing that the integer and fractional quantum state, they can get this kind of rather different type of the AC response out of it. And often that this AC response is one way that you can detect kind of various insulators properties. And all times, people are interested into especially these Wigner crystal formations and pinned Wigner crystals and those kind of things. And it has been kind of revisited kind of multiple times. And most of these experiments, however, it's rely on the relatively large size of sample, right? Again, this rule of the game here is that if the size of the sample is large, and then you can have the even large inductance in the inductance measurement, or in type of capacitance measurement, you have the large capacitance. So measurement is a little bit easier and kind of the most straightforward. Now, difficult part that we are dealing with in the graphene type of the experiments is that the sample is a smaller size. So again, you need a little bit more kind of trick to do that. But at the same time, the advantage we have here is that we have the gate voltages, and not only magnetic field, but gate voltages that allows us to kind of tune kind of wide ranges. So there's a kind of price that we have to pay because in the small sample and it's a little bit more challenging experimentally. But then the award we have is basically, well, you know, that you can just kind of measure this as a function of magnetic field and gate voltages. And often this will give you a little bit richer the signal. So here's a kind of device structure. So here's a graphene sample that we just kind of do the kind of DC measurement. But then we have this kind of gates. You can see that this gate is in circular with the small trenches and separate for the other part. And for this RF measurement, we don't necessarily need to the DC coupled sample, especially if you're interested in the capacitance of the channel. You can capacitively couple your device, and this will allow us not only graphene that we can quickly extend these experiments with many other systems where the contact resistance is not necessarily need to be great. The other part of this experiment is basically we are just doing the Covino style of the measurement. Especially this is useful and important for the quantum Hall type of the devices because just to do the regular Hall type of the measurement where the edge state can carry the current, both the DC and AC, this make the kind of life much more difficult to analyze. So we prefer to have the of the device such that between these two AC electrodes, we are mapping AC response. There's no direct connections through the edge state between these two electrodes. I think that's kind of another part, right? So the measurement itself is very similar to the last time that I present, except that now, since we are measuring the capacitance, that you have to reconfigure that your so-called matching circuits such that you deliver the most of the RF power to your sample in the capacitive way. And the response that I'm measuring, the RF response reflectance measurement, is designed to be sensitive to any small capacitance changes or the dielectric changes, the dielectric response changes in the experimental capacitance changes we expect. And so that's why that you have to redesign your matching circuits and simulate this matching circuits. What is the right elements you just put up there and so on. And but the idea there is if you just kind of do the right matching, when the sample reaches a sample capacitance changes, this resonance curve that you will get onto the RF reflectance changes the amplitude, the resonance frequencies, as well as the width, and all these things is kind of sensitively depends on to the change of the capacitance that you are measuring. So that's kind of the way it worked it out. So this measurement I'm going to show you is a little bit still kind of under the developing. So I don't have the really strong conclusions, but at least kind of give you that flavor that what experimentalists can do here, right? So here I'm showing you that basically again the spectrum that we are measuring the reflectance, that this is a frequency that we are sweeping, and this is a gate voltage we are sweeping, and this color map shows simply that amplitude change of this resonance that we are measuring to the complex circuits, right? And that there's a resonance there, and then note that there's a zero magnetic field. I sweep the gate voltages, that my Dirac point is somewhere there, and you can see that there's some minute changes of the resonance frequencies as well as this width. Again, that throughout this the RF simulation, one can extract the sigma 1 and sigma 2. By the way, sigma 1 in my notation is say sigma that we are measuring, omega is a complex number, is sigma 1 plus I sigma 2. So this is a real part and this is imaginary part. And this is basically something that we got interested in, right? And in some sense, you just do the measurement right, that sigma 1 and frequency we are measuring is about several hundred megahertz, which is kind of in terms of the electron dynamics, that's kind of DC type, quasi-DC measurement. So in these cases, so we expect to see the sigma 1 that we should measure is very similar to the what you just do the DC transport measurement. Indeed, sigma 1 you are seeing here, more like below that the minimum here and going there, and this is my Dirac point. More or less it behaved right. Now, once you just kind of go into the higher magnetic field, apply the magnetic field, the signal do changes, right? It's clear that in the original signal that there's kind of a lot of the oscillations that kind of picks up, right? And again, there's kind of small changes of the resonance frequencies and the width and the amplitude. All this kind of allows us to kind of extract both the sigma 1 and sigma 2, right? And that's why I'm saying that the AC measurement is immediately much richer because we have the kind of much more information that you cannot get from the DC, right? And you start to see that their behavior is kind of rather different. But let me just kind of pick up some of these things. There have this large oscillation is possible because I think this is a relatively small magnetic field, and then you can see that Subnikov-Das oscillation, it eventually come into the quantum Hall states sample quality is extremely good. Therefore, that we get the already 4 Tesla well-developed quantum in all the ranges. As you see in this blue curve, which is a sigma 1, the real part of the conductivity. Real part of the conductivity is zeroed out here, right? And at the same time, that now imaginary part actually do something interesting, right? And as you go to the high magnetic field, we start to see that all this symmetry broken on the level start to shows up. If you look at carefully, there is even fractions that kind of shows up. So sigma is much, much richer, right? Now, if I just stack them together, both the sigma 1 and sigma 2 as a function of gate voltages and magnetic field up to 9 Tesla, can clearly see that quantum state kind of appears there. The blue curve, sigma 1 is a really good guide, where the quantum plateaus appears and quantum plateaus supposed to appear in the middle. And what you're seeing here is a sigma 2, that imaginary part capacitive response, do start kind of changes as you go to the increased magnetic field. For example, that it start kind of increases that supposedly in the kind of quantum plateau regimes, right? And as you go to the larger magnetic field, they also do show some of the interesting part of that. The first thing that we can just do that is that just focus on the integer, the quantum states, and then simple that symmetry unbroken, the integer quantum states there, and then ask that what can we see that why that their signal got increases. And in fact, that signal got increases is something that related with the, I just kind of mentioned, that effective Chern number increases. Now at the fixed magnetic field, indeed those the sigma 2 value got increases is more like what is expected from this is a Chern insulator, and then the capacitive response, the dielectric response is actually the kind of depends on this Chern numbers or effective Chern numbers in this case, and that more or less what we are seeing experimentally here. But of course, the signal is much richer. For example, here that there's kind of interesting shapes and those kind of things. And to understand that, we have to go kind of beyond that. In fact, those kind of nice shapes around here potentially is related with this some sort of Wigner crystal formation of this in this particular Landau level. Even further, if you go inside of this in between this plateau regime, then of course you start to see that this fraction start to develop there, and the sigma 2, the dielectric response actually shows much rich behavior. So any kind of detail of the analysis here, but simply you are seeing that it's a much kind of the richer the physical properties there, and it's basically to be just kind of interpreted, right? So again, that my thesis here is now you are dealing with an insulator. It's a kind of, we are measuring the kind of the bulk of the quantum states, right? And we know that there's an insulator, if I just don't deal with that kind of energy state. And then we are asking that what is the dielectric response of that insulator, right? And that's basically kind of what experimentally kind of assessed here, right? So I think that's supposedly my second lecture that give you a little bit of flavor. That once you just go to this more of the AC measurement, I would say more dynamic measurement, and this provides us kind of much richer information. And it used to be experimentally very challenging, and then only limited access of the experimental method was possible. But in some sense, that the technological development, many of this type of experiments is now in the scope that we can access. Now, technological development is kind of interesting part. That when I was a graduate student like you, that there are a few things you want to avoid. That I think if you just ask that your senior students, and then often the comments I heard, I had from my senior students, just don't go for anything using division fridges, because back then half of your time. But now I think there is basically kind and you can buy it, and if it's something a fix, you just kind of call up the company and they will kind of send you a module that you can replace it off. So that is kind of, the other comments that you had is, all right, so avoid anything about the high frequencies beyond that 100 megahertz. Because you know that once you go experimentalist that go beyond 100 megahertz, I think there are a lot of the the experimental technique is needed and instrumentation becomes extremely expensive, or you have for the 30 years, I think that got changes. It's really expensive, but it's reachable. And guess why? Can you guess why? What made the yeah. A lot of the instrumentation you can get for cell phone work in this kind several gigahertz, right? You can get it from the off-the-shelf instrumentation. So I think make the many experimentalists' life easier. The many exciting experiments kind of comes around. I believe that the directions can go even just kind of gigahertz ranges. I think this is where that qubit community usually work it out. That frequency is now pushed into the tens of gigahertz. Some special cases of the gigahertz is ranges, and you can see that now that's the ranges. Now you start this with the terahertz side where the optical techniques comes down. So finally, that I think this experimental community start kind of covers kind of really wide range of the dynamic measurement. Okay, that's the second part. All right, so I have a kind of 45 minutes. Oops, what am I doing? So let me move on to, without delay, next topic. So original topic that I had was the correlation measurement, coherence measurement, but then I think given that restriction of time, I will just kind of confine myself to kind of only one topic and kind of discuss about that topic. More generally, that somebody asked me questions that what is a way that we can measure coherence? I think say, for example, electron-electron interactions, electron scattering times, and those kind of things. Traditional way that one measure in mesoscopic physics is mapping some sort of localization behavior because the localization, either strong or weak localization, although it was induced by the disorder, often that contains this interference caused by the disorder, and measuring the localization phenomena often is a good way you can access the coherence time, particularly electron action coming up. But of course, that is a more disorder effect. Another way that you can measure coherence is basically building up your device such that coherence actually can be detected. And one way you can just do that is the building up the interferometry. And the really widely used technique onto the building up the interferometry in the solid state the device is using the quantum Hall effect. And that's basically something I'm. And because I've been working on the graphene, I will just focus on soon that the quantum interferometry in the graphene. Okay, so this work is again that with the collaboration between my group and the Amir Yacobi's group, but the main driver of this experimental Tom Werkmeister, who just graduated, and strong support from the theory of the Bert Helper and the Dimar-Feldman. Okay. So let me start with kind of general idea that why people got excited with the interferometry, especially in quantum interferometry. And goal that often the people are raising now is can we actually measure the anion, and that's kind of based on kind of following idea. Now, if you have just any quantum mechanical identical particle, of course, exchanging this identical particle, that you get the different features into your two-body wave function. If it is fermion, that after exchanges, you get the negative sign. If it is boson, you don't get the sign changes. And that is kind of really dictative of the system. And there's no way that you escape that any of the fundamental quantum particle, either fermion or boson. That statement is only true for the 3-dimension. Once you get into 2-dimension, in principle, this can be a different possibility. It's different statistic is possible. And part of the reason is in the 2 dimensions, by just this exchanging the particle, which is related with just kind of breaking these 2 particle positions, is kind of related with the winding numbers of this operation, or the braiding operation. And in the 2 dimension, this braiding operation has a kind of well-defined topological invariance and defined by the winding number. And that allows us to have the different type of possibility of this statistics. And depends on to the where the ground state is, the degenerated, non-degenerated, one can actually, after braiding in the 2-dimension, that you get the kind of different type of braiding phase of this abelian anion cases. If it is the degenerate ground state is degenerated, even just after braiding, you get the unitary operation, the connect one to the other, turn into that kind of non-abelian anions cases. But the bottom line here is that in the 2-dimension, there's actually possibility that you have the different type of this particle, the fundamental particle, they give you the different statistics. So that is kind of exciting, the physics. And of course, this, especially once you just realize this non-abelian anion, including Majorana, basically not only is the braiding statistics kind of studying that, just braiding will just give you that the possibility to store the informations in the non-local way that topologically protected. So that becomes kind of quickly important technological issues nowadays, right? Now, I think that's let me skip this one. One of the fertile ground of the looking for these anions in abelian or non-abelian is a fractional quantum of states, starting from the Laflins wave functions, and then the community quickly realized that many of these fractional quantum of state, if it is kind of Jane sequences, that the excitation of those the quantum the state can be described by the anions, and then using this composite fermion theory, that you can quickly show that any of these kind of fractions that you have, the excitation of this quasi-particle excitation of the fractional quantum, the ground state can be expressed by the fractionalized charges, as well as their the anionic braiding statistics. So in other words, that basically change the exchanges there. The two quasi-particle, you get this the exchange braiding phase of the pi of the 3 for the nu equal 1/3. If it's 2/5, fractional charge of the 1/5, and the braiding angle is something like this, and so on, right? So that's kind of one part. The other exciting part is, let's go for the so-called the quantum of states. Now, this even denominator quantum of states can be viewed as a pair of the composite fermions ground states, like the superconductors. And that excitation here is supposed to be even the fraction. And the braiding statistics becomes this non-abelian, and you expect to see that quite unusual kind of braiding statistics, even in all type of defect after braiding. So all these things kind of make the proving the anionic nature of the composite fermion states becomes kind of quite exciting field over the past probably 25 years or per se, right? So the question here is how just kind of prove these things. The fractionalized charge can be proved by just looking at the Schoen noise, for example. That is a kind of really seminal work done by Moti-Heiberlem's group. Just looking at this Schoen noise coming from this one of the fractionalized quantum of state edges, and they can show that indeed this quasi-particle that carried through this edge state of the fractional quantum of state can be in terms of this fractionalized charges. But how about braiding statistics? I think that has been kind of really the one of the important issues for many years. And one way that you can just look at this kind of braiding statistic or the phase is basically you can detect a phase, and this requires the kind of coherent measurement. And the you can think about what is the simplest coherent measurement you can just build up in the solid state system is basically using the Aharonov-Bohm effect, right? Say if I have electron or any charged particle, by the way, the passing through this two different paths split by the beam splitter, and if I thread the magnetic field that couple with the charged object, and if you just recombine and simply build up this interferometer can detect this phase of this two different paths, and that phase is also kind of modulated by the Aharonov-Bohm flux that we just kind of thread into this path, and that's the expectation. This first, the really experimental realization of this experiment was done by just kind of putting solenoid and sending this particle through the back. But the state of the demonstration was done in the 80s. And this is kind of one of the beautiful experiments done in the 85. And I believe this was done in the IBM, right? Yes, yeah. What this experiment shows you in the technology in the 1985 is about the time that people can use the electron beam lithography. People now kind of fabricate very small structures out of it. And what they did is they kind of patterned these gold rings, size about, I believe, 100 nanometers, and that ranges, right? And then measure simply the resistance across this gold ring and apply the magnetic field into the system, and they see the resistance is oscillating. And this oscillation period is, of course, related with the atom bomb flux that thread in there. And this is a way that you can do that. Let's kind of look at this phase. Now, this experiment worked it out because this size of the ring is small enough and the temperature of this measurement is low enough such that electron that pass through the ring has at least kind of phase coherence across this path. And that's kind of one of the key that this experiment worked it out, right? So seemingly that what we can do here is to do these experiments with a quantum system, right? So this is one of the very early experiments, that really seminal experiment, okay, done by Moti Bloom's group. What they did is basically they patterned their two-dimensional electron gas such that they can define the well-defined the quantum edge state path in there. So that's basically the devices got patterned. But there's a kind of really important ingredient of this. The structure is basically the splitter called the quantum point contact. Basically, the way it works is you bring these two quantum edge states close by through this pattern or that gated quantum point contact, and bring them so close by so they start to scatter each other and tunnel from each other. And that's a way that you can so-called partition this edge state. And in the optical analogy, that acts like the kind of beam splitter. And by controlling this gate voltage, you can just control the efficiency of beam splitters. And topological, the connection of the edge state with the beam splitter, in fact, is very similar to the so-called Mach-Zehnder interferometer in optics. And instead of you just kind of detecting that intense change of the light, here simply you just monitor what is in your detector, just get this the interference. Now, interference pattern, that constructive, destructive interference can be controlled by controlling the phase. And here the phase control is simply by applying the magnetic field and applying the magnetic field into that area, which actually constitutes the atom bomb, the phase, can modulate it, that conductance in the system, as well as that you can just change the gate voltage on the side, change the size of this interferometer area, which also do modulate its atom bomb phases. So typically the experiment was done by the gate voltage versus the magnetic field. They can see that this constructive or destructive interference is modulating, and that kind of beautifully show the atom bomb effect. And that's the integer quantum Hall effect kind of modulated. While this interferometer works okay, it's a little bit difficult kind of make. A little bit easier to make this interferometer that done by the many group, including again High Bloom's group, Charlie Marker's group, and other groups, is so-called the Fabry-Perot interferometry. Here, that the idea is again the two beam splitter that the quantum edge state deliver carriers into the cavity, but then before it goes out through another beam splitter, it can be kind of circulating around inside the cavity multiple times before it is escaped. Depends on the transmission coefficient of these two the point contact. You can control how long that the charges stay inside the interferometry. But nevertheless, in the end of the day, you just get it out and pick up this atom bomb, the phases between them, again modulating this atom bomb phase by the gate voltage modulating the area as well as magnetic field. You can see that this modulation got modulated out, right? So in some sense, there are the multiple different design of the interferometry, and you can just measure the interference between this the carriers going to the two different paths. Now experiment seems like they're really straightforward now, because instead of the integer, you set the sum of the fraction, you should be able to get the phase information, and especially if you have control of the number of the anyons or the quasi-particles inside of the cavity, simply you can just kind of expect to see that sticks out this type of measurement. While that statement is straightforward and easy, you can already see that there are difference. This is around the 2000, right? This is about 10 years from there. But 10 years of the differences, a lot of the other experiments, and from here to another 10 years, a lot of other experiments. But experimental realization of the measuring anion braiding phase has been really, really challenging for 20 years. And it only appears around the 2020 that indeed kind of first evidence that indeed braiding is possible. Now, you may ask that why it takes so long time, right? It's not simply because the experimentalist is lazy. So these experimentalists I just kind of introduced is a really the first class the experimentalists with a lot of creative ideas there. The problem is the controlling that so-called decoupling between edge state with the bulk. And the difficult part is coming from that the interferometer I just present here, the quantum Hall-based interferometer versus the interferometer on the gold, there's one big difference. And that's a problem for the struggle for 20 years. Anyone guess that what's the difference? There are many differences, but that critical difference. The critical difference there is the gold, basically interferometer pattern, the path is set, right? Was basically gold, the lines that we just draw, right? Changing magnetic field, we are not changing anything, right? But in the quantum interferometer, yes, it is probably look like the sample boundary, the edge state is there, but in some sense, when you just tune the magnetic field, every time so you just change the magnetic field such that you just change one magnetic flux quanta in your device, you basically need to plug into one more electrons in there, right? And when the electron gets in there, and especially it starts kind of deform the edge states, you can just kind of push the edge state or that kind of pull the edge state. You effectively, unless you just design your device such that when the additional electrons in there, that additional electron will not deform the path, right? You get kind of different. Every time you change magnetic field, you not only change the amount of bond phase by just area times B, but that adding the magnetic field to change the electron will also change the orbits, becomes kind of complicated, right? And that's kind of the part. And you have to come up with a device design such that additional electron I plug in that changes magnetic field with the area, and that's kind of what you need kind of put the device design. And that comes around about 20 years to realize that what is the right design to do that. And once you do that, in 2020, that this is that there are two experiments actually shows that indeed the braiding phase, the measurement is possible. The first one comes from the Michael Manfras group at Purdue. They basically make the very similar the Fabry-Perot interferometer, except that in this underneath of this device, they carefully put the right the amount of the screening plane in there, such that even if you change the magnetic field, plug the another electrons in there, another charges there, quasi-particles there, it does not change the area of this defined by the interferometer. I think that's kind of key. And when just they do that and measure this interference pattern with the magnetic field in the gate voltages, the stripes coming from the ion bomb oscillation I just mentioned is appearing. But then from time to time, there's the phase slip appears, right? There's kind of the slips appears. And that the phase slip is kind of about the 1/3 of the phase slip, which is kind of expected coming from the the exchange braiding statistics that expected in this type of the measurement. So I'm going to discuss that part a little bit more, a little bit quantitatively, but let me put it kind of for now in this way. Another experiment was complete kind of different type of approaches. It was done by the Favre's group at the Paris. This comes following way. This experiment is a little bit more dynamic type of the measurement of the workshop. They have this a little bit complicated structure, but essential part is they have the one important quantum point contact that kind of different edge state and just kind of redistribute it. So with this kind of quantum point contact, you can do the following experiments. You can send one quasi-particle and another quasi-particle at the quantum point contact. They just scatter it off and just kind of propagate in other directions, right? And this is often called this anion colliding experiments. It's in some sense, it's kind of close to the Hong-Wu-Mandel experiments in the quantum optics. So in the Hong-Wu-Mandel experiments, basically use the center two forces, and whether you go into the kind of bunch it in one directions or that kind of another directions or separate it out. There is kind of interesting the correlation of the scattered photons onto the beam splitter. And if you kind of want kind of understand the bosonic nature, there's kind of always kind of tendency of the bunching, right? Now, just with our anions, and they have the kind of anion statistics, exchange braiding statistics, which actually dictated that once they kind of scattered off from this beam splitter, just measuring the correlation from the downside, you can see that what is the braiding statistics of those kind of the particles colliding. It involves a little bit more complicated math that I don't understand. Basically, that's kind of analogies. But nevertheless, out of this the cross correlation measurement across this beam splitter, they actually get the information what is kind of braiding statistics to anions, and that's kind of two different experiments, but about the same time that provide the very tantalizing evidence that indeed at least kind of 1/3 quasi-particle you braid, and then you get kind of right answer. I think that's a kind of good starting point. So once we see this type of experiments, then of course the people like us that are working on the two-dimensional system, especially graphene, we have the strong incentive. Well, maybe we can just repeat this experiment using the graphene. The graphene quality becomes almost comparable to the highest quality of the gallium arsenide. I think mobility is approaching the millions nowadays, or even close to 10 million. So it is kind of only factor a few lower than the best gallium arsenide sample. But even more so is basically the graphene with the regional magnetic field and the control, you start to get this a lot of the even denominator states very strongly. And turns out that in the graphene, the form factor of this wave function is different, as well as this or other the interaction parameter is different. So even denominator state in the graphene, which actually is important, even denominator quantum state, which is a kind of eventual goal that everybody has, is much more robust than what you see in the gallium arsenide. So energy scale of even denominator is something like a 10 Kelvin at the 10 Tesla, which is about the order of magnitude larger than you see in the gallium arsenide. So there is a kind of quite interesting incentive that we want kind of continue in this type of the experiments. Device structure is something like this. The one difference between gallium arsenide and graphene here is in gallium arsenide, you have the gap, band gap, which is several hundred millielectron. So you can use this gap as a kind of nice way that depletion carriers and define your device, define your quantum dot. Graphene, especially single gap, so to deplete the carriers, you have to rely on that certain gap of the Landau level, such as the nu equals 0 gap. So which means that we need kind of define our device with many different gates, but that's kind of the possible. So here's the device structures. One can just do that, and one can guide this quantum states and kind of through this the pattern, the top gate. But most important part is those kind of this the quantum point contact, where that you can again bring these carriers that collide them each others and doing that. And some of the version of the experiments, we can start to see that this nice oscillation there. And let me skip all these things. For the integer, we get this nice result. and that the integers, we get this kind of very nice result of the oscillation. And now you start to see that we can do the experiments even with the cases that two edge states kind of flushing through. But then you can start to see that there's kind of phase jump is related, it appears there. And that phase jump is indeed kind of, let me skip this one. Phase jump is related with if I have that, just, let's say that using this one to explain. So here that we have the two quantum edge states flowing there. That I'm just kind of partition the outer the edge states, right? And then look at this interference outer edge state. Here the inner edge state is completely separated, right? So it is kind of separate from the out there. It looks like just kind of the quantum dot, if you want, ring shape of the quantum dot. And if we just kind of measure the interference onto this integer quantum state, what you see here is that there's kind of phase slip appears onto the quantum states, right? And the phase slip is along this line that we just kind of have. Now, on the same experiments and the device structures we have, if I just show you the previous slide, we have the separate gate that only control this the quantum point contact. So everything is fixed, but we can simply just control this quantum point contact, the potentials with this top gate. And in that way, I can just kind of make this partition. Everything is fixed, but except that now I just kind of let the outer edge state is passing through, not interfere at all. But I'm just going to start to couple this inner quantum states through this the quantum point contact and measuring the interference along this the inner edge states. Now that is basically what you're seeing, that the Arnold-Bohm patterns we have, right? So compare with this one, basically we have the a little bit wider separation, which means that I'm dealing with a probably smaller area, because it makes sense because inner quantum state is kind of inside, right? The area is kind of small, but there's no phase jump here, right? Because there's nothing inside here, right? The reason that I'm just comparing this one is just look at this, comparing this one, that where we have this Arnold-Bohm effect, we have that basically that's kind of where the phase slip is appearing there, right? What does it mean here is that when we have this geometry, in other words, there is the reservoir that carries the charges inside, that the phase slip appears whenever the inner states shows the Arnold-Bohm effect, which means that as you're just kind of changing this magnetic field, I'm just increasing the electron numbers one by one. As I said, one Arnold phase is basically the one more electron, right? That is coincide with those kind of phase slip. The whole point I'm just trying to make here is just phase slip is inherently related with some of the charge states is occupied inside of the quantum states. That basically that's an example that I'm going to, yeah. We can just change the magnetic field in a wide way, but you have to change the corresponding gate voltage, staying the same filling fraction. Yeah. In this one we're dealing with just a nu equal 2. Just a 2 integer quantum state. I'm just showing this one that even for the integer, when you just generally when you see the phase slip of the interference, that is related to some of the kind of charge state occupations in there, right? So that's kind of what, yes. Oh yes, yeah. So there are many things. If you just can go through the really wide range of the magnetic field, there are many other things going on, including that at some point you can even just lose your QPD control, right? So typically and ideally, let's see. Let's look at, for example, right? Ideal case that magnetic field and gate voltage ranges that eventually that because A times B is a constant, right? But then the gate voltage will change this one. So it's inversely related, but that if I just kind of look at certain area, it is kind of more like the linear regimes that we just choose. So I'm just kind of choosing only small ranges of this one, where that this curve is look like the linear, right? No. I think phase slip is exactly related charge state inside of the cavity got changes, right? So that's kind of point I'm just trying to make. And maybe I better actually use this one to explain. So you can just do the following analysis that along this kind of phase slip, that you can see how much phase slips you get here, right? And detail of the electrostatic analysis that tells you that this phase slip is related with the amount of charges you just kind of change in your cavities in there, right? And that's kind of the kind of one important point can be made here. So this phase slip is related with this occupation of the charges inside of the cavity. Where the visibility is reduced? So kind of during the phase slip happens, right? Okay, so that's kind of what you're saying. That's kind of this transition ranges, right? I would say. So indeed, right. So ideal cases, it is kind of really sharply, you have the oscillation going there and basically sharply jumped in there, but everything's smeared out there. So it looked like kind of losing the visibility experimentally. But I would say that maybe I can, and the other data that what is really happening there. Okay, good, yeah. Okay, so the point I'm just trying to make is now if you have the right the interferometry here, then that you start to kind of see that this phase slips. And indeed, put into the right geometry, this phase slip contains information about the occupating that quasi-particle inside. Now, let's try to repeat these experiments that into the fractions. That's basically kind of eventually what we are doing. So experiments I'm going to show you is a kind of rather similar experimental situations that what Michael Manfra did into gallium arsenide, which is kind of done in the graphene version. As I said, typical graphene sample, mobility is pretty good. And you can see that kind of bunch of the fractions. We started with these fractions, well-defined fractions, such as 1/3 or 4/3, one of the kind of Jane sequences, and choose that. And unlike the gallium arsenide, we have the wide range of the gate voltages and magnetic field can be tuned. So that allows us a little bit of the wide range of the experiments. So what do we expect to see? Okay, so this is the kind of geometry, the cartoons of the experiments, right? We partition the quantum energy state, especially now we can put in the fractional quantum states in that kind of everywhere, right? And this the plunger gate will change the area and the change in the magnetic field. Then we both kind of look at the atom-bomb phase, and this from this phase that we should extract some of the information. So what is information we want to extract? First of all, that whether we can see that the charges are fractionalized, and second part is whether we can just pick up this the braiding phase, right? So the way that we can just kind of look at this one is, of course, look at the atom-bomb phase, and that will contains atom-bomb, the oscillation, the period will contains this normalization, renormalization of the fundamental charges, and we expect to see the 3 times of the larger the phase modulations once you get into 1/3 of the fractionalized charge. But how about this braiding statistics? Braiding statistics requires that we need kind of occupied inside the cavity with the some of these anions in there, right? For integer state, I just showed the ring like this inner states. It's clear that basically I have the reservoirs there. For fractions, we don't have that, but hope is there enough number of this the site of the anions, and then as we just kind of sweep through our gate, this anion site got trapped, occupied, and we should be able to see the phase slip. Indeed, that's kind of what the Manfra's group actually see this one. They see that this phase slip corresponds to this braiding phase, and this phase slip appears into the kind of somewhat random fashions that whenever there is the impurity states got filled up, they are seeing this kind of phase slip in kind of such a way. So that's kind of experiment kind of we want to do in the graphene. So when we just kind of do these experiments, we'll get pretty much disappointing, the very first set of the data we are obtaining. So the graphene interferometer we created is a really high quality for integer, and we are seeing that kind of all these nice interferometer behaviors and all this kind of partition, the inner and outer states. And the previous data I showed, I think it was kind of really as good quality as you can see in the gallium arsenide, even better. So we had the kind of higher hope that we can immediately get similar into the. But unfortunately, when we just look at our data is based on this. So this is the data that we just take all these interferometers. Everything's fixed, magnetic field is fixed, gate is fixed. We simply monitor that interferometer output as a function of time. And we expect to see that this conductance is constant, but instead of constant conductance, basically this signal is jumping around, right? And often this is kind of what experimentalists call the random telegraph noise, means that somewhere in your device there's a switchers, right? And that basically this switcher is randomly on and off, something like something is occupied and unoccupied randomly. And unless you get rid of this one, usually this is kind of garbages, we have to throw it away. But then Tom, who just graduated, and he first kind of looked at this data, and then I said, Tom, that, hey, this is a garbage device, we have to make another one. He was saying that, all right, well, I can make another one in a few months. But before doing that, look at this data. It was not just a simple two-level random telegraph noise, but there's if you just look at there are 3 levels, right? And note that this is 1/3 of the quantum of states. And in principle, that you may have this the 3 anionic states, right? If it is occupying 3 anionic states kind of randomly, it's natural to see that there's 3 different levels of the signal. Okay, there's a plausible assumptions, but it's difficult to prove in that way. So I thought, hey, I still insist that you better make the new device. But then just to say that Tom said, well, look, I think that I didn't change anything yet, right? So what if we start kind of changing something? So what Tom did the next time is that, now while this random telegraph noise is there, so you can make the statistics where that this 3 levels, but start to change something. For example, they're changing gate voltages and fixing the magnetic field. And then what he saw that is as a function that it's this gate voltage you have the 3 level, but when you change the gate voltages, those kind of 3 levels that you're seeing is basically kind of changing. And each of these 3 levels shows a kind of really intertwined sine waves. And each of the sine wave is exactly 120 degrees away, right? So just looking at this data, just the histograms, the data here, immediately tells us indeed his original proposal was right. I think there are at least a kind of individual anions gets in there, and whenever anions gets in, that you get the signal is jumping around. But nevertheless, if you just make this the gate sweeps and make the statistics, we can just get this indeed 3 different branches of the sinusoidal curves there. In fact, this is kind of what is expected that from the theory for some times. Already, indeed, kind of all times people are thinking about that. Indeed, if you have the traps into your the fractional quantum state in the interferometer, if the trap is randomly occupied and there's some dynamics in there, you will have this kind of the sinusoidal branches. It just kind of switch around, and that's kind of what kind of this kind of data kind of seeing that. In a sense that kind of this switching event is fast, then you see that this branch is changing one to the other one immediately. However, experiments, we cannot just do it infinitely fast time, then there's a smearing. So brief moment of this, the visibility kind of decreases happen, right? So that's kind of what we are seeing. So at least we can see that there's a braiding phase can be detected in such a way. Now, can we do that, the atom bomb phase type of the measurement? As I said, that integer, we can just do this beautifully, the atom bomb measurement, and the slope will give you that the charge that we can get in integer quantum O. Same experiment we did into the fraction basically doesn't work it out, because even without any changing of the magnetic field, our signal is really random, right? It looks like the random because if you just kind of make the cut of each time cut, there was kind of phase slip is frequently happens, something like every 10 seconds, we get the phase slips. And that's kind of difficult to make this type of curves that with this change of magnetic field. But nevertheless, as a whole, that if you make the statistics, as I mentioned to you, that we have this Fibonacci appears at the fixed magnetic field, right? So instead of the individual the curves, we just change the magnetic field. We take the statistics and the change of magnetic field, and see that this branches start kind of the changes, and the slope of this one is basically 3 times of the integer slope. So we can even show that the charge on this interference is also kind of fractionalized. So that's kind of nice. So that's something that we can just study that, and one can study that what is nature of the traps. You can just kind of look at how that the switching rates got changes with the temperatures and voltage ranges. So let me skip all these things for now. You can just look at this, how that the telegraph noise got changes over the time. And you can get this kind of how many the trap site and what is the distributions roughly get out of this one by just analyzing the noise, the telegraph noise spectrum. I'm going to skip these things. With the temperature dependence, you can get kind of somewhat informations out of it. But nevertheless, I think that we know that there's some sort of a few random traps inside the device that created those the telegraph noise. I would say that while this telegraph noise in the beginning is rather annoying, it was actually also kind of somewhat blessing for us that effectively measure these exchange statistics. The reason I say that is there are kind of 2 other experiments about the same time that we did these experiments appears, kind of different groups. The first one is basically Yuval Ronen's group at Weizmann University. You look at their devices exactly the same as ours, because Yuval was my former postdoc. So we smuggled the interferometer technologies from the Weizmann group because Yuval did a PhD, but then we exported our graphene technology to Weizmann. So it's fair. But their device, I think Yuval's device it's probably much better. And look at this, there's a kind of beautiful patterns appears into these bone phases, but they don't have any the phase slips, right? And then getting out of this the exon braiding phase is a little bit difficult with this the regular pattern. Now the other group here is Andre Young's group, and at Santa Barbara. They make this device different structures, but nevertheless they just work on those 1/3 and look at them, and they have this also phase slip. But for them, basically this phase slip is there, but it was not the time scale is much longer. So doing the statistic out of this to make that kind of the histogram was very difficult. It takes a year to do that, right? So somehow 10 seconds-ish of the phase slip that we had was kind of rather lucky, right? Yes?
Do you know where this time scale 10 seconds is coming from?
Yeah. So where it comes from? Why other groups actually didn't have this the annoying the phase slip, but we did, right? Turns out that we borrowed the fridges from Ami Yakubi's group's wet fridges. So it's old fridges, but it was well filtered. So we thought it was a good thing, so we can try out, right? But this is old fridges compared with the other groups, right? So their shielding is not just bolted into the lowest temperature of cryostat. It's bolted into the somewhere that about Kelvin or 700 millikelvin of the shielding. So you can see that my device see that kind of black body radiations coming from about the Kelvin, right? So there is a kind of fire photon is showering down to our sample, right? And potentially that will give you the jolt of certain anyons to jump into the patterns in there, right? So how do we prove that? Well, simply that this is our sample box. We just kind of covered the sample rather tightly with a specially designed filter, right? And then those kind of the phase slips are all gone. So we know that I think it's a kind of bad shielding we had. But nevertheless, it was lucky, right? And then after we just do that, that's all gone. Okay. I have 0 minutes, so I will probably stop, but give you some over our loop. Okay, so where we are going in general in this field. So the next important part onto this game is basically, can you just really control the occupation of the design the anyons or the quasi-particle inside of the cavity? Right now, that everybody's, including us, rely on the little bit of the random traps in there, right? Potentially, we can just kind of build in that even just IR antennas there, the antennas, we can activate it by just kind of sending the control the radiation. But even better one is if you just kind of build up some kind of anti-dot, which can be controlled against the gate, such that we can control the numbers of the occupation of the quasi-particle inside of the cavity, such that I want kind of induce this phase slip that whenever I want and how much I can want. I think that's kind of important part, kind of next technology. I believe that this technology is not far away. There are many groups that I mentioned here, as well as others, kind of working on heavily to do that. And what else? Then of course, since at least a billion anyons, you start to see this the phase statistics. Next thing one can do that is going for non-abelian anion in the graphene. As I said, even denominator state in the graphene is much stronger than gallium arsenide. With say 10 Tesla magnetic field, you can get the rather robust of the even denominator, the quantum states put into the interferometry. By speaking about this, by the way, this is not just the plan. Indeed, Yuval Ronen groups they posted a paper a few weeks ago, about 2 months ago, I guess. Actually, no, it was already 5 months ago, just before the Christmas, by the way. It's kind of it ruins my mood of the Christmas. But they actually had beautifully demonstrated now the same interferometer work at even denominator states. So it's there now, right? So I think seeing all these things, finally the community, either gallium arsenide, the graphene, 2D material in general, they bring these anions into much more controllable ways on the site. And already kind of DC type of the measurement is beautifully demonstrated. I already hinted that some control can be done with the deliberately sending the lights in there, the excitations in there. French groups measurement, you see, it is more now measurement. You can just imagine the time type of the measurement and look at this dynamics of the anions there. So I believe that in the next few years, this field becomes quite rich because the technological development becomes kind of quite rapidly happening here. All right, that's all kind of I prepared. Thank you very much for your listening. Yeah. Okay, so obviously that kind of there are other fractional challenge later, or right? That's next exciting part. My view there is to get this type of the physics be done, or engineering can be done, the quality of the quantum is extremely important, right? And it takes gallium arsenide 20-some years, even though the gallium arsenide is extremely clean sample from the starting point. It takes the graphene about say 20 years per se, because the refined quality kind of about the time. So the quality of the sample is extremely important to realize this part. So I think given that the many fractional challenge later just appears in a few years, I think they give you the really kind of rapid progress, but still that I'm seeing the quality of the sample is not up to the level that we can control there. The quality of samples and quality of the contact you can make and all these things will take a little bit of time, but in principle, yes, why not? I think this could become rather exciting directions to go.
I'm just wondering whether you can share your abelian anion plane is now identified. And as far as I remember, abelian anions are always like quantum computing and, making like promise with this like dream,
Non-abelian anyone, you mean? Yeah. Sure, yeah, of course. I think, yeah, that's a that's kind of this defensive plot that you can find in Scientific American many years ago, right? I think they accompany this. In fact, the Microsoft first they come up with their Q station they're aiming for this topological protected quantum computing. The first part of the project that they funded for probably about 10 years is actually this, right? So, but simply was too early. Now I think they may actually come back onto this one. I don't know, but there are many other platforms that can realize the non-abelian anyons. So I'm not sure whether this is really sellable still, but I mean that there is a theoretical proposals there, and the now at least kind of few realized. I know that many people just kind of didn't think that this is still kind of too believable, but if you just look at the this is Waals' experiments. Waals is, by the way, someone that starting from the 2000s that pushed this idea for 20 some years. I mean, he made the kind of really interesting the progress based on the gallium arsenide, and they're seeing that some of the tantalizing result as well. I would say that there are some still kind of way to really solidify the proof there, but there has been some of this idea they're pushing around that whether indeed this even denominator non-abelian anion, the quantum states, that whether you can just kind of turn into the more like the qubit type of the device operation. I'm not sure whether that will be eventually useful, but at least one of the goal of this community is to realize those kind of device operation. Theory-wise, there is already kind of well-defined the theories there. So it's more like the engineering is needed for this part, right?
Related to Junkai's question, what goes wrong with the interferometry when your sample is not clean enough?
So the major part is the quality of this QPC. As you see that the most important part of the interferometer is basically the beam splitter, quality of beam splitter. Now you can see that the QPCs consist of this the edge states getting close by, and so the thing like the 10 nanometers to the 15 nanometer, 100 nanometer, that is basically critical. That you can mix these quantum edge states. So you can imagine that if that area, there's disorders and other things messing around, I just lose the control of this beam splitter. Basically, that's kind of where that things get kind of extremely wrong, right? So the very first step that one kind of see that is whether you can construct a beam splitter that worked as kind of as you control. I think that's kind of first demonstration kind of anyone needed. Yeah.
What is this anti-dot, and can it be moved around?
So yeah, okay. Anti-dot versus dot, I think that's already bit of the jargon. But anyway, so that's where that is a little bit different from the other bulk, such that the quasi-particle or quasi-hole can sit in there. It is quasi-particle, then it becomes dot. If it is quasi-hole, it becomes anti-dot, right? But nevertheless, I think that's a way that I can start kind of populated some quasi-particle, quasi-excitations. Yeah.
Is there like a hope of like moving these regions around and actually grading?
Yeah, so idea that is basically this dot or anti-dot is where that I can populate this the anyons there. Once it's there, it doesn't matter whether it's moving around, not moving around, right? Whether that they are localized compared with something that I can circulate it outside. So that's kind of important part, right? Because that number got changes, that will be kind of changing the braiding phases, right? Yeah.
What if you wanted to use them?
Use them for fuse them. Yeah, okay, so fusing them, okay, let me see that. Used to remember that how this working. It's not just moving these things around, but idea here is, let's see. Yeah, in these languages, I forgot that how it worked it out. Yeah. In fact, this operation with this one is a little bit different from typically kind of Majorana, that operation. Part of the reason is that this rely on that basically there's a two different quartz particle, E of 2 and E of 4. And of course, that's already make the kind of things difficult. I cannot just kind of reproduce what's there. But if you read these papers, I think they just described how does it work. Yeah.
Antidote is because there's some local defect or like local variation of the spectrum, is that right?
Yeah, that's right. Yeah, yeah. But eventually, when we say the dot, means that we want kind of deliberately control that by electrostatically by using the gate. Yeah. Okay.